In this video, I'm going to demonstrate the radio transfer program in the SpecPR system. Specifically, I'm going to show the command line interface and how to make scripts. I'm going to compute a simple one component spectrum and then a two component spectrum. Okay, I have two windows set up, and I have very little screen real estate because I'm making this as a 1080p video. Normally I would use much larger windows. So I set up a directory that has a SpecPR restart file and a SpecPR file that I can write results to. These Java routines are for the next video to make a to illustrate the GUI interface. Right now I'm just doing the command line interface. I have another directory where I have my optical constants, and I have my optical constants here, and I have some support files here. Now, Radtran does not assign files or directory. That needs to be done in SpecPR. So we have a restart file here. Restart files are simple ASCII files, and we have our test file assigned. We have the optical constants assigned and our support assigned. So first, this is all set up. If you need to learn how to set those up, there's previous videos in the headquartered SpecPR series that'll show you how to do that. So I'm going to, if we needed to start SpecPR, and I always use an alias, run SpecPR, and DSpecPR is the latest developmental that has all the newest features. At the moment, most of the time, like on PSI's PAN spectroscopy computer, DSpecPR and SpecPR are the same. And on my laptop here that I'm doing this, they're the same, so it doesn't matter. The Xterm 2 is a double size from the default, and it makes a pretty large window for viewing spectra. Unfortunately, with a small screen real estate, there will be overlap here. So you can see we have the SPS 0000 file and the 01 file assigned, and our test assigned. So we don't need to do anything else in terms of setup, and we can go ahead and start Radtran. And similarly, I have an alias set up so I can quickly start these programs. So starting Radtran, restart file, the X terminal, X window size if you want something larger than the default. Okay, so we see that we have our files assigned. There are multiple options here for computing reflectance spectra of multi-component mixtures. Generally, the capital R is what I use. It's got some of the latest features that the lowercase r is an older version and doesn't have embedded intimate molecular and aerial mixtures. The way we're going to run today, this will default to the R. If you want to do layered components, here's a two-layer mixture which has all the features of the capital R plus layers. If you want to compute in another medium, for example, this was developed for oil in water, but could also work for like a spectrum of a rock where you have mineral grains embedded in quartz or something like that. This is more experimental. The equations look solid. Initial testing has been done, but I have not computed a rock spectrum, for example, and compared it to an actual measured reflectance spectrum of a rock. So if you're interested in that, we can work on that. If you want to derive absorption coefficients from a reflectance spectrum, use this. And then this is an older unmixing routine, which I haven't used in quite a few years, so we'd have to look at how it's working these days with other changes and make sure it's still okay. So for now, there's also different options for how the computations are done, and these describe. You can look at Hepke's 2012 book, page 59 and page 60, or the 1981, to see how the grain internal and external reflections are done, and that has to do with solutions for Snell's law. So for now, we're going to do capital R. Now, before, let me remember in spec PR, a X is a hard exit. Go back to the beginning. We're also going to record all our commands. So if you do a greater than sign, and we'll just call it model 1. And if you want to, it's a simple ASCII text file. You can do .text, but in general, you don't need that. So this will record all the commands that we enter, and we can play them back at another time, including modifying the file, so that effectively makes a script. So we're going to do capital R again. We're going to compute reflectance. The only option here is a 1. This is a placeholder for other options. The wavelengths. So we need to know the wavelengths. So let's print the spec PR files are binary, so you got to run a program to view them. So the wavelengths are in record 6. So, and remember, if we go back up to the beginning, SPS 000 is assigned to the letter V. So capital V6 are wavelengths. We don't need to delete any channels. We're going to do a one component, so a pure surface. So 1, and I should be adding in comments here, and I'll do that for this point. So S and a comment, single set of N and K. So this says the real index of refraction. So we're going to do H2O ice. So that's these two spectra right here. So the index of refraction is 51, V51. We should say what it is. So one way to do this would be to just copy the whole title, at least up to there. That's the important part. Then now it's asking for the absorption coefficient. So that is V62. Now we have the grain size in centimeters. That's 50 microns. The weight fraction, since it's just one component, it doesn't matter what this is. So the weight fraction has to be 1. And the density of ice is about 0.95. I don't remember the exact value, but that's pretty close. It doesn't matter since it's a single component. So we should comment this. Okay, now the angle of incidence and emission, or geometric albedo. I commonly do 0 degrees incidence and 30-degree emission. We'll want to normalize. What this does is it computes a Lambert surface that's a pure scattering surface and makes that a reflectance of 1. Otherwise you'll get 1 over pi if you want. So we're really computing reflectance factor, not the reflectance, which maxes at 1 over pi. In the Hepke equations, there's an S value for scattering. The default in the program that works for many situations is just fine, so we press return. We should have commented that. Grain size dependent parameters, so the S value increases slightly as you go to shorter wavelengths, because shorter wavelengths are more susceptible to scattering. So we'll use the default here, and let's see. Okay, so the calculation is, most of the calculations are done. We can skip the first surface reflection if we want for a case where you have a non-particulate surface, but the surface is say glassy smooth, and the angle you're viewing, you wouldn't see that first surface reflection. So we want to include that. So no NF. You can add in an aerial mixture, but we're not going to do that. Then an output title. So this is a 50 micron grain size. There's a history that gives all the detail, but if you're doing, you can fill up the title. You have 40 characters, so I equals 0, E equals 30. Those are the main parameters. And SpecPR carries a database of different types of spectra. So if you include CMP REF for computed reflectance spectra, that'll be cataloged and you can find it later. Or you know when you see an H2O at 50 microns, and I should have said what the 50 microns is. And you could also spell it out, grain size equals 50 microns, but soon as you get more complex, you'll run out of space in the 40 character title. It's good to know that this is a computed spectrum as opposed to a laboratory reflectance spectrum of an actual sample. Okay, here's our spectrum. Let me change the scale, 0 to 1. So there's the spectrum computed from down in the UV 0.2 to beyond 6 microns. The question is, do we want to have a comparison to another spectrum? Let's see. So here's let's do the B ring spectrum, and that was SPS 0001 was assigned to you, so and so 141, and over here is the wavelength pointer U6. So the red spectrum here is the B-ring spectrum. Now you see these are very, very different. It's actually curious that they match out here, but not at the shorter wavelengths. So there's something that brings the reflectance down from from the pure ice spectrum. So we can go ahead and write that. So if we exit, and we're going to write to SP test 1, so W, and then put the history into W also. So now we're back to the beginning. So we can, if we do greater than sign and return, the recording of all that data is now closed. So we can write to another file. You can Control Z spec PR and look at what we just wrote. So here's all our commands as we type them in. So we can now modify these, like change the grain size and other parameters, and then read this back into Radtran or spec PR and have those commands executed. But so I Control Z that through the program in the background. If you type jobs on a Linux machine, you see your job, FG foreground. We're back to the beginning, so we didn't have to exit the program. So we're going to do this again, only this time we're going to Model 2, capital R, V6 is the wavelengths, no deleting of channels. Okay, we're going to do a two-component mixture, so type today. Okay, now we need to go back to our okay, we want to do our crystalline ice here. So the index of refraction is 51, V51. Absorption coefficient, V62. We're going to do the 50 micron grain size. We're going to do a different weight fraction. We're going to do 0.98 and 0.95 for the density. Mixture 2. Okay, now for mixture 2, let's use carbon. So the let's see, index of refraction, V95. The absorption coefficients, V106. And now the question is how large grain size. Let's do 5 microns. The weight fraction is 0.02, and we'll do a density of 1. I don't recall off the top of my head the amorphous carbon density. You need to look these things up before when you want to do precision work. Okay, and I should have labeled that. We can go and label that after the fact. The angle of incidence and emission. Normalize. Default there. Okay. So there's debugs in here in case you see some funny numbers. We can investigate what the factors were. Okay, number of aerial mixtures, 0. Now we have H2O. There's a couple of ways we could do this. Let's try 0.98 H2O. 50 microns plus. Now we could say 0.02, but that's implied. So we can just say carbon no, it's not. It's 5 microns. Okay, just fits. I see I made a mistake there. Okay. Oh, look, I didn't plan this. Change scale. So now we see that the adding in the carbon has really brought down the reflectance level. We approximately have the reflectance level right in this, and these two main ice bands are approximately correct. I mean, they need to be just a little bit deeper. Looks like we have a good agreement out here. We have a mismatch here, and one thing to note, you'll always see this as being too low, right at about between 3.2 and 3.4 microns. That's an error in the optical constants that needs to be fixed in the optical constants, so don't pay attention to that. We obviously didn't match this decrease. That's some reddening compound that is in Saturn's rings, makes them look yellow. So while we got the albedo right, we don't have the reddening agent. So that requires some other a different compound that's not ice and not carbon. But this gives you a good idea of how to compute these. There are two other things of note is that while we have the band depths here approximately correct, we don't have this correct, and we have hardly any 1.04 micron ice band, and a very weak 1.25 micron ice band. And that's due to, it's clear once you understand layered media that the ring particles in particular are layered media where there's fine-grained ice on top of larger chunks of ice. So a layered media calculation wouldn't be able to do that. No intimate mixture can match all of this and all of this. This also is, this discrepancy in the shape here is due to some submicron particles. So there's multiple grain sizes that are needed and layered media in order to fully solve the matches to all the wavelengths here in the infrared and then reddening in the UV. So if we want to save that, we exit the plot, type in that we want to save it. We want to save the history, and then we're done. We're back to the beginning. Hit greater than sign, and that closes the command file. We can now exit Radtran, and we can look at Model 2. So here's all of the commands that we entered to run this two-component model. What I would do would be to edit that and make this a little more readable by moving some of the comments around. Yeah, let's go out to here. But you get the idea. What is that? Oh, I had some fat fingers are getting other keys here. But you get the idea. The other thing is this greater than sign, that's not needed in a script that terminates the command input, so delete that line. Now you could then at this point change parameters here and then change the title and run another model. So you can do those much quicker than going through the menus by hand each time, where any time you do things by hand, there's a likelihood of a mistake. So scripting helps reduce mistakes, and it also gives you a record of exactly what you did. Okay, so I mean that gives you an idea. You can obviously get a lot more complex. Also, the scripting can be up to 10 levels. So while when you're in SpecPR or Radtran, to read this model in fact, let's do that. You just, oh, that's in, I did SpecPR, not Radtran. You'd say less than and that file name, and that reads all the commands from that file in. Now if you accidentally inserted a line, then the commands would be out of sequence and it won't produce the right result. So you got to be careful when you're editing. If you want to add a line for a comment, let's say you want to add a line here, put the \# at the beginning of the line, then it'll skip that line with that, and so it won't displace the command sequence that for the incoming commands. And you'll see this kind of stuff in Touchquarter in the expert system commanding. You'll see these comment lines. So be sure, if you want to add a comment where it doesn't is invisible to the command processor in the program, then start the comment at column 1 \#. Okay. You can turn a lot of things into variables, and then you can call these as subroutines. So in here, we could take out some of this stuff, and if you want to call another subroutine, you just say less than sign, and whatever you want to call it. So you can do pretty sophisticated commanding, and you'll see these kind of things in the Touchquarter expert system where different subroutines are called depending on what the size of the spectra are for different cases. Okay, I don't need that, so I'm not going to keep that one. That's a reasonable introduction to the commanding and the different models that are possible. You can run through and explore on your own a lot of the different options. Just follow the prompts. They should be reasonably clear. If they're not, shoot me an email and I'll see about improving them if something isn't completely clear. Okay, and with this I'll end this video.